Hey there, in this video we are going to look at how to find the zeros of polynomials. And to get started with this, we need to start with a theorem. If you're wondering what exactly does it mean for something to be a theorem, well, it's basically like a rule that says, well, if something is true, then something else will also be true. So think of it like a rule that's been proven to work for all of the conditions in that if statement at the beginning. So this one is the remainder theorem, and it says that if a polynomial f of x is divided by x minus c, the remainder is going to be the same thing that I would get from taking that c and plugging it into the function and evaluating it. So it seems like kind of a crazy thing that if I divide it, the remainder is the same as just evaluating at that value. So let's see if we can kind of convince ourselves that this is true with an example. So here I have the function f of x equals 7x squared minus 5x minus 8. And we're going to see what happens when we plug 1 into the function and then when we would divide by x minus 1. So first, let's take 1 and plug it into the function. And what we get for this should be the same thing we get from the remainder by doing synthetic division with that x minus 1. So if I plug in 1 to the function, 7 times 1 squared minus 5 times 1 minus 8, that all simplifies to negative 6. Okay, so if I set up the synthetic division for this function using x minus 1, then I should get the same value that I just got, the negative 6, for the remainder. So I'm going to take the 1, stick it in my box, and then list the coefficients along next to it. So 7, negative 5, and negative 8. Then I'll put a bar below a ways down and drop down my first coefficient. So the 7 goes straight down below the bar. And then I take the 7 and multiply it by the number in the box. So 7 times 1 is 7. And I'm going to add that to the next coefficient. Negative 5 plus 7 is 2. And then multiply that by the number in the box. So 2 times 1 is 2. And add that to the next coefficient, negative 8, gives me negative 6. So I got the same value for the remainder as I did from just plugging in the function. So depending on what I'm doing and what I need as a result, I could just plug in a value to find out what the remainder would be or not. Now this is particularly helpful because what we're looking for are the zeros of functions. And so there's another theorem that's going to help bring all this together for us, and that is the factor theorem. And this says that for any polynomial function, f of x, if x minus k is a factor of the polynomial, then f of k is going to be 0. And the same is true in the other direction. If I plug in a value k to the function and I get 0, then that means that x minus k is a factor. So this can be really helpful. If I'm given a value and I just want to know if x minus k is a factor, I can just plug it into the function and see what function value I get out, rather than having to go to the trouble of doing the synthetic division. So it can be a real time saver if that's the only information we're looking for. Now let's do an example where we can kind of put this to use. So here I'm asked to use the remainder theorem and the factor theorem to determine whether x plus 3 is a factor of f of x. And if it is, then they want us to come up with the factored form of the function. So let's start out by seeing if we can figure out whether x plus 3 is a factor. The fastest way of doing that is to take the number 3. I'm going to take the opposite sign of it because all of these theorems have said x minus a number. And I'm going to just plug it into the function. So if I take negative 3 and plug it into our function, which we have the function f of x equals x to the fourth, minus 4x cubed minus 14x squared plus 36x plus 45. So I plug all of that into my calculator, and sure enough, I get 0. So that tells me that x plus 3 is actually a factor of the polynomial. And so the next thing they asked me to do is to write it in factored form. Well, I know it's a factor, but I haven't figured out what's left over after I divide the x plus 3 out of this function. So that's exactly what I'm going to do, is I'm going to divide this. And because it's an x just plus a number, I can use synthetic division here. So I can avoid the hassle of long division. So I'm going to take negative 3 and throw it in a box. And then I'm going to list out all the coefficients of my polynomial. This one's got a lot. So 1, negative 4, negative 14, 36, and 45. And then I'm going to get going with my synthetic division. So I draw out my bar, drop the first coefficient down, the 1, and then multiply it by the number in the box. So 1 times -3 is -3. Adding that to the next coefficient, -4, I get -7. -7 times -3 is 21. 21 plus -14 gives me 7. 7 times -3 is -21. And then I add that to the next coefficient, 36, I get 15. And 15 times -3 gives me a -45, which is good because my last coefficient is 45. So adding those together, I get that remainder of 0. So what this has done is found me all of the coefficients of the polynomial that's left after I divide out an x plus 3. So to get that polynomial, I'm going to take the degree of the original polynomial, which this was a 4th degree polynomial because it started with x to the 4th. And I'm going to lower that degree by 1 and throw these in as my coefficients, counting down from the x cubed. So 1x cubed minus 7x squared plus 7x plus 15. That's what's left over after I've divided out the x plus 3. So writing this in a factored form looks like this here. Now this x cubed polynomial that's left over could be factored further. We're going to keep going in this section in class to learn what do I do to find all of the real zeros of a polynomial. But for now, practice these couple of theorems and using them to start factoring out terms and identifying zeros below this video.